Hello everyone. In this short presentation, I'll be talking about stress-induced leakage in 3D NAND flash memory. I'll be showing some characterization data, present some analysis, and possibly technique. So here's the outline. First, I'll talk about a little bit of motivation and background of studying silk. Then I'll show our experiments, procedure, and the hardware setup. And we are using both flavors of 3D NAND flash memory, floating gate and charge trap. And I'll ask very specific and three important questions. The first one is silk dependent on memory state? Does it depend on the layer positions or the position on the deck in the 3D stack? And most importantly, can we mitigate or heal it? So first, why 3D NAND is so important? 3D NAND is everywhere. Consumer devices, AI data centers, automotive, even a space. Reliability failures are not actually theoretical. For example, this Tesla eMMC failure that shows the real consumer impact in 2018. And another example could be the failure of Curiosity rover, which highlights the mission critical risk. So as the density of 3D NAND increases, even small reliability concerns can lead to larger scale catastrophic failures. Now, modern 3D NAND flash scales vertically a lot. So it all started in 2014, where oxide scaling saturation and few electronic statistics forced industry to move into 3D NAND. So what happens nowadays? In 3D NAND now we have high aspect ratio etching. We have CMOS bonded array where the memory cells and the CMOS circuitry are directly connected from top to bottom. We have dual deck or multi-deck processing, and even we have QLC memory where one cell can store 4 bits of information. So eventually we have 16 different VT distribution possibilities. Now what hasn't changed in this 3D NAND development, and that is the oxide thickness. The oxide thickness has not really scaled, and because data retention is dependent on oxide thickness at the end of the day, long-term data retention will be the final barrier in the next future. Now, what is this stress-induced leakage current we are talking about? So here I'm showing a planar floating gate flash memory cell. In floating gate flash memory cell, the storage node is polysilicon, which is metallic. So the electrons are residing on the surface. Now, at the end of its life, the tunnel oxide is degraded and they have numerous defects in the tunnel oxide, which is well studied in context of silicon dioxide. These defects can be positive, neutral, or even negative. Now, what happens is silk originates from this stress generated or aging related oxide defects. How? Because these defects enable trap assisted tunneling paths. Over time, electrons can percolate through the oxide even at low fields. Prior work by Yelmini, DeGrave, and Lellis explains this well for planar devices and MOS structures. But for 3D NAND, especially with this new vertical geometry and more layers, this behavior is still poorly investigated. So that's why we're in. Here's our experimental setup. We use a custom built hardware setup. We can interface raw memory chips, which are commercial off the shelf, and we can communicate with the chip through our workstation. And this is how we do our experimental flow. We cycle an array of memory cell a couple thousand times, which emulates the aging behavior, and we store some data and eventually read it at room temperature from time to time. So if a cell is leaky, that will show up in our retention test, and that's how we characterize silk. And of course, as I already stated, we are using both flavors of 3D NAND chips, floating gate and charge trap. In floating gate, the storage node is polysilicon. In charge trap, the storage node in red here is silicon nitride. And one important feature of silicon nitride is this storage node is shared among the 3D NAND stack. Now, silk in 3D NAND. So here first I'm showing on the left VT distribution curve for a group of cells that has been cycled 5,000 times and monitored over a month. And if we closely follow the 1 month curve, 1 month CDF curve, we see a huge anomalous tail, and this is a classic signature of silk, which means a good percentage of cells are leaking because they're cycled, their oxides are damaged. So this is a confirmation that silk exists in 3D NAND floating gate memory cells. And why this massive leakage happens is because in floating gate, as already I said, that electrons reside mostly on the surface of the metallic polysilicon layers. So even if a TAT path or silk path exists, there can be a massive leakage, like a chain of loss. If I overlay now the results, the same results for a group of city memory cells which have been cycled for 5,000 times as well and monitored over a month, let's follow the black curves which are representative of the CT cell. Now this array of cells, interesting that the VT distribution have a huge median shift, which is probably because of the lateral charge migration, because this in silicon nitride layer, the storage node in silicon nitride in charge trap memory, they are shared among the cells. So it is very well known that with time the stored electrons they dissipate laterally. So that actually may create this huge median shift. But there in the black curves there is no anomalous tail with time even after a month, which means these cells they don't have actually silk, they are not vulnerable to silk. So CT memory has negligible silk, and that can be related because of the storage material silicon nitride, because the silicon nitride the electrons are in very localized traps. So electrons very close to the silk path can leak, but others actually stay in their localized state. So a big problem for CT memory. Move on to 3D NAND flash floating gate memory. So what about the state dependence, as I already asked in the outline? So because these are all TLC memories, I have shown here the CDF curves of the cycled 5000 cycled group of cells of the floating gate 3D NAND cells, and here I have plotted the CDF distributions of all different program states from L1 to L7, and this is very noticeable. Then the L7 state is mostly vulnerable to silk. The other states don't show this kind of anomalous tail. And if we increase the number of cycling, the silk tail elongates, and with time the silk tail elongates as well, indicating more and more loss. Now, how about this dual deck 3D NAND stack? Nowadays, dual deck technology is employed in depositing the 3D NAND stack. First, certain number of layers are deposited, oxide and word line interlayers are deposited. Then tapering channel hole is etched to form the channel throughout these layers. And then again, another set of layers are deposited and another channel through it, and ultimately this from these two stacks these channels are connected. Now this lower one is called the lower deck, the upper one is called the upper deck. So nowadays in 3D NAND employs multi-deck technology. There are even chips commercially available which have 4 or 5 decks, and this is done to reduce this tapering shape of the channel and to introduce more and more layers successively, so that we have now more than 300 layers of memory cells. So 3D NAND stack has significant process-induced variability in the oxides along the layers because of this channel hole tapering and deposition temperatures and whatnot. Now, so my question is there any layer dependence of silk, or is there any deck dependence of? So what about the layer dependence of silk? So I took a group of cells from the lower layers of the lower deck of the 3D NAND floating gate memory cells, which I already said are 5000 cycled, and these are 1 month retention. So the CDF curve shows that not all layers behave the same. Lower deck cells and the lowest layer cells show significantly higher leakage. So this can be because of two reasons: process-induced variability during deep stack fabrication, or thinner effective oxides in the lower layers because of the tapering shape of the channel hole. On the contrary, if we look at the upper deck, there's not much significant silk. So this means silk or leakage, stress-induced leakage, is not just a device issue. It's a process architecture interaction-based issue as well. And this layer and deck level asymmetry matters, and it matters which data is stored in which layer of the memory. So this is important. So lower deck has high leakage due to heavily pre-existing oxide traps or poor oxide quality maybe, and the lower layers have higher leakage due to thinner oxides because of the tapering shape of the. Now silk can be healed. So here's one interesting plot. So we collected the VT movement of a group of cells over time, over like 3 months, and we identified 3 groups of cells: stable, and which are mildly leaky, and extremely leaky. But it's interesting to see that even the mildly leaky and extremely leaky cells, they're slowing down with time. Now my question is, can this slowdown be a recovery effect? So let's do an experiment. So here I have again cycled a group of cells 5000 times. Then I kept them in room temperature without doing anything for 25 degrees Celsius. And then I stored some data in it, and then I kept in the room temperature those data as well for 10 days and 25 degrees Celsius. So, and in between these two retention tests, I have collected data from time to time. Here's the retention comparison of the first retention and the second retention on the same plot. So the cells in this red curve, they're still showing silk this between these two retention. In the first retention interval, they had huge loss. Even in the second retention interval, they had huge loss. So which means they are leaky on the first retention and the second retention. But the cells under this blue curve, if we look at it, they're pretty interesting. They had huge shift in the first retention duration, but they now have very minimal shift in the second retention, which means during the first retention, some of the cells may have been healed at room temperature. Now let's do something better. So this is very well known, annealing the oxide defects through thermal baking. So here we again did the same experiment, but between these two retention tests, in between these two retention tests, we added a baking session, 30 minutes at 120 degrees Celsius. And we're expecting that that will improve the situation. So here's the results. So if we add a baking phase between these two retention tests, that actually changes things a lot. If we now we see that there are a lot of cells now under the blue curve, because a lot of cells probably have been healed because of baking because of the baking phase, and there are a very small number of cells that are still showing silk. Now what happens is that during these baking experiments, because I already told you there can be different kinds of defects, there can be positive, neutral, or negative defects. Now these neutral traps, they may become annealed and ultimately become a defect-free state during baking or this retention interval, and the bonds may have formed, and now the silk path has broken. So baking at high temperature can actually accelerate silk healing process. So let's do something different, because this is not a traditional MOS device, because we can now store data in the gate oxide. So we can either store electrons in the gate oxide, or we can either keep it in the erase state during baking. And let's see how it behaves depending on the state when it was baked. So in the first group of cell, we cycled 3000 times and monitored over a month at 25 degrees Celsius. In the second group of cell, we again cycled 3000 times, but before monitoring them and pre-programming them, we added a baking session, 30 minutes at 120 degrees Celsius. And for the third group, we again cycled them for 3000 times. Then we kept them in programmed state and baked them for 30 minutes at 120 degrees Celsius. And then we monitored them over a month at 25 degrees Celsius. The basic difference between group 2 and group 3 is that in group 2 they were baked in erase state, and group 3 they were baked in programmed state. Now how does the results look like? So these curves show these three different groups of cells, and it's interesting to see that the cells that are baked in programmed state, they have much less leakage. Now, baking in P state can better reduce the number of heavily leaky cells. Now, how can it happen? So, here's the possible scenario. So, a cell in the programmed state during thermal baking. So, they have neutral traps, they have electrons in the oxide, electrons in the floating gate, and everything. And with time, these neutral defects, this bond can be formed and they can be a defect-free state. But what happens when a cell is in erase state? Now, because the cell is in erase state, there are a lot of inversion electrons in the channel. Now, these inversion electrons can come in the neutral defects, and actually they can destabilize these neutral defects, and the neutral defects can actually become negative. So in E state, inversion electrons dominate, and these neutral defects, they cannot go back to defect-free state maybe, and they become more like a negative trap state. So there is not much real annealing of these defects. So these erase state cells show much less annealing. That may be a reason. So in summary, silk is better in charge trap memory, and silk is especially critical for L7 state in floating gate memory. and floating gate cells mostly in the lower deck suffers from silk, as we have already shown. And interestingly, silk shows better healing when floating gate memory is baked, keeping it in programmed state.